live. Hi everyone, looks like we're live. Welcome back to Cambridge University Astronomy. Welcome back to another Wednesday evening. I'm afraid this week it does seem like it's cloudy, so we don't have stargazing for you, but we are going to make up for that with a very excellent talk from our headline speaker. I'm here with Dr. Vid Iršič from the University of Cambridge, and he's going to tell us all about dark matter. So with that, over to you, Vid.
Okay, thank you, Matt. So what I'm going to talk about today is trying to tell you something about how we learn things about dark matter, how we learn about the properties of dark matter by studying the universe. And I will begin first by really trying to explain one of the methods that we use that in the last decade has been leading the frontier of our knowledge on the properties of dark matter. And then I will lead from this into what are the different models that we can constrain, what are the different things about the dark matter that we can learn from the universe. And hopefully this will be more intuitive way than just telling you what we know about dark matter. So with that, I'll be off, and first thing I'll try to explain this picture that's in the background here that sort of illustrates how we actually observe dark matter. So astronomers over the past couple of decades have grown very good at telling everyone that we have many different pieces of evidence for dark matter in our observable universe. But perhaps it does not do any harm to just review some of them, just to highlight that we can really probe dark matter, that we can really see evidence for dark matter from very different regions in space. So starting off is something that is very close to us, our own galaxy. In particular, there are stellar streams in our galaxy that tell us something about the distribution of dark matter in our own galaxy. And further out, we can look at nearby galaxies and look at how they are rotating and their velocities, rotational velocities. And this was actually the first piece of evidence almost 60 years ago now by Vera Rubin that led to the discovery of dark matter. Further afield, we have faraway galaxies, and what we're mostly interested in there is whether these galaxies are distributed in the universe randomly or not, and how many of them are closer together versus how many are further apart. And then very, very far away, we can see the remnants of the Big Bang called cosmic microwave background. And we can play a very similar game that we do with galaxies, also with the cosmic microwave background, where we are interested in how the temperature of the cosmic microwave background in the sky varies as a function of the angle on the sky. One key ingredient here that has only recently started to attract attention is the fact that the space between galaxies is not completely empty. There is actually stuff there that we can observe. We call it intergalactic medium. And it has turned out that it's surprisingly good at telling us about dark matter properties. So most of the rest of the talk, I'll just talk about how we can use intergalactic medium to learn about dark matter. One thing that I would like to highlight before that is that galaxies and intergalactic medium are both connected in some way. They're both part of the density and matter in the universe, and they trace the same kind of structures. So when we measure positions of the galaxies in the sky, or when we measure intergalactic medium, what we're really studying is this cosmic web, this filamentary structure that is basically distribution of the matter density in the universe. And this includes all matter, including dark matter and more common variety of matter, such as protons and atoms. And really, by studying the intergalactic medium, we are studying more these filaments rather than these knots and halos in which the galaxies live. So we're more interested in these filamentary structures, these tiny things, and these void-like regions where there is very little atoms and very little matter there. So to understand how we can study intergalactic medium, we have to understand a bit what is it. Unlike galaxies that emit light, intergalactic medium on its own does not emit any light. So it's a bit harder for us to really observe it. But what saves us that instead of in emission, we look for signatures and we look for intergalactic medium in absorption. What I mean by that is that between us and so on the other side of the intergalactic medium is some backlight, and between that backlight and us, there is this matter that the backlight illuminates. And as it illuminates it, we will be able to see this. For the purposes of our studies, we often use quasars as this backlight, but that is simply just because quasars are by far the most luminous objects that we know of in the universe, so we can really see them very far. But people have been doing these things with galaxies as well. But the main point remains the same. These quasars or galaxies provide the light that is illuminating the intergalactic medium. And as the light travels to us, if we have something in the way, the most natural process that occurs is that the light gets scattered, and it's scattered off path so that there is less light arriving to us. And we can detect this and we can measure this. What exactly is the scattering process and what exactly happens in the intergalactic medium very much depends on the ingredients of the intergalactic medium. And for the most part, intergalactic medium is composed of hydrogen, some helium, and very small traces of some heavier elements. And what we're mostly interested in is actually neutral hydrogen, neutral gas that is between these galaxies. And of these neutral hydrogen scattering processes, the one that we study most is called hydrogen-Lyman alpha transition. For those of you who are more interested in that, this is the transition between the ground state and the first excited state of the hydrogen atom. But for the purpose of how we actually study this, it does not really matter. So we are interested in this scattering of light due to this hydrogen that lives in the intergalactic medium. And a very important aspect to realize is that if there is more hydrogen between us and the quasar, we will see less photons, less light arriving to us. And vice versa, if there is less hydrogen, we will see more photons and higher transmission. And this is something that is one of the main ingredients that we use in these studies. Another ingredient that is important to realize is that if there is more hydrogen, this hydrogen will live in a deeper potential well of dark matter. So there will also be more dark matter where there is more hydrogen. And it's a very important step to make that from lower transmission, less photons that we see, it means that in the path of those photons, in the path of that light, was more dark matter. Now, I've illustrated this as there is only one intergalactic cloud somewhere between us and the quasar, but that's actually not really the case. What we have is many atoms, many hydrogens between us and the quasar in the background, and we see many of these scattering processes. What would be ideal would be if we could tell not only that there was a scattering happening, so that there is some dark matter between us and the quasar, but also where exactly in the universe, how far away did this scattering occur. And to understand this and how the universe sort of provides us with a solution for this, let's sort of look at this bottom left sketch that I'll present. So between quasar and us, there are all these intergalactic medium clouds, these hydrogen atoms, and light travels through, and if it hits these clouds, it scatters. The bigger the clouds, the more hydrogen there is, the more the light scatters. So this red line is basically illustrating the amount of photons that arrive at Earth, sort of how much light, what is the intensity of light that arrives to us. With higher values on this line indicated that more light arrived, and less light arrived where there are lower values. And these lower values indicated there is more dark matter there. But what is also true is that if we split this light that comes to Earth into colors and count how many photons, how much light came at the blue end versus the red end, we can tell actually what was the distance to these scattering processes. In particular, there is a very direct connection between what is the distance from Earth to these scattering objects, these clouds, and whether the light that we observe is at the blue end versus the red end of the spectrum. And the basic reasoning behind this, why this is possible, is because as the universe expands, it also stretches and expands the photon wavelengths. And this is what allows us to really measure the sort of, and map the density and the structure of the matter, dark matter, in this sight line towards the quasar. And this is how we can map the cosmic web using intergalactic medium. And this turns out to be a very, very powerful probe to understand and really measure the properties of this cosmic web for different dark matter models. But how does this really then connect to these dark matter models? That is perhaps the more important question to ask. And to understand this, we should start the perhaps simpler question: what really is dark matter? And while astronomers can be very good at telling everyone that we have evidence for dark matter, we are in more of a pinch when it comes to explaining what actually dark matter is. We have many theories, but we have no evidence for any of these theories to be correct. However, some of these theories are better at explaining observational evidence than others. In particular, if dark matter is some kind of particle, these sort of theories are much more interesting in some regard. And this is because of two main reasons. One reason is that our particle physics friends tell us that the standard model of particle physics is not yet complete. And a lot of the extensions of this particle physics model include particles that could very well be dark matter. On the other hand, a more trivial, perhaps, sort of reason why dark matter as a particle is a good candidate is that if dark matter really is a particle, it makes it much more easier to explain all the different phenomena from our own galaxy all the way to the cosmic microwave background with a single model. And this is something that a lot of the other models struggle with. So for the rest of this talk, I will talk only about particle dark matter models. And to sort of plunge right into it, I will show here a sort of presentation from a dark matter conference I attended a couple of years ago, where it shows all the different models that are particle-based that people are considering these days. And these are all theories that are to some degree viable and sort of agree with the observed data. But what is perhaps the first striking feature is that this is like a zoo. It's like coming into a zoo where someone has ordered all the enclosures of the animals in alphabetical order by their Latin name of the species. It's very hard to understand what is going on here. It's very hard to really get a grasp of which of these models are doing something that we can observe, which of these models are based on what underlying physical principles. So instead of trying to explain all the models here, I will instead focus on explaining a few of them in terms of something very simple, which is the mass of the dark matter particles. And the reason why I'll be doing this is because it turns out in the end that we are very good at measuring this, and we're very good at telling particle physics colleagues that dark matter cannot be less massive than a certain number, for example. So the way I'll try to do this is I will order dark matter models and dark matter particles by its mass, with lighter particles on the left and heavier particles on the right. And instead of talking about the mass of these particles in grams and kilograms or electron volts, I will instead just show where some of the more common variety of particles lives, like electron, proton. There is a more recently discovered Higgs boson is one of the more massive particles. And on the other end, neutrinos are the lightest particles that we know of in the standard model of particle physics. So to add to this ensemble of typical particles, we add a cold dark matter model. In general, investigations that are conducted within astrophysics and cosmology, we often talk about the standard, the dark matter model. And by that, what we mean is something called cold dark matter. These are particles that are heavy, heavier than a proton typically. And one other aspect is that they were produced thermally. By that, I mean that in the early universe, when the cold dark matter or when dark matter was produced, it shared the energy and the energy spectrum of the other particles, so that they were somehow connected in the early universe. And what is striking about this cold dark matter and why it garnered so much interest over the years and became the standard cosmological dark matter model that we use is because if this dark matter, these high masses, is weakly interacting with the standard model of particle physics, then it turns out that no matter what else, it predicts exactly the values of dark matter as measured today, the abundance of dark matter as measured today, which is around 24% of the total energy budget of the universe. People call this sometimes WIMP miracle, referring to these cold dark matter particles as WIMPs, being weakly interactive massive particles. And many of the theories in particle physics that predict these particles reside within the realm of supersymmetries. However, it could be that the universe did not actually create a cold dark matter particle. And the simplest thing that we can do is we can say perhaps the mass of this particle was lower, but I'm keeping all the rest of the assumptions the same. So this lower mass will be characterized as something that people call warm dark matter. But this warm dark matter is still in thermal production in early universe with the rest of the particles such as electron and proton, so it has similar energies in the early universe. And to understand the difference between cold dark matter and warm dark matter, it is perhaps useful to go back to these dark matter gravitational potentials. Cold dark matter particles are heavy, so their velocities are relatively less important. And their velocities being less important means that there can be a lot of detail, there can be a lot of structure in these gravitational potential wells of dark matter. There can be equivalently a lot of structure in the amount of hydrogen that we see in the intergalactic medium, there being bigger clouds, more massive clouds, or less massive clouds around. Whereas the warm dark matter, on the other hand, because the mass of this dark matter is lower, but the same energy, this means that the velocity, its velocity will be relatively more important. And because the velocity is higher, it smooths out, it smears out all these details, and all we are left with, and we can really see, is some big potential well, as if there was no detailed structure around. And this is sort of the basic principle that how we can use the cosmic map to really distinguish between something that is a warm dark matter candidate versus a cold dark matter candidate. Sort of another way to think about this problem of cold and warm dark matter and their velocities is as if you are cycling through Cambridge or on foot, and you can explore the town in very much detail. You can go to the Bridge of Sighs all the way to Jesus Green, all the way to King's Parade, and you can check all the streets and all the shops. But warm dark matter has a much larger velocity, and it's much like going up north on M11 in a speeding car, and all you see of Cambridge is a town up there, not much detail. So this is sort of the difference that we really want to observe, and this is the difference that we can distinguish in the data. And as warm dark matter models go, one of the most prominent candidates for this is sterile neutrino, which is related to our usual neutrino that we know through a theory called seesaw mechanism. This theory seeks to explain why neutrino masses are so light. And this is another viable candidate for a dark matter. And there has been a lot of effort in investigating this sort of regime of dark matter. And what we can really say from observing the cosmic web of the intergalactic medium is we can start putting the most stringent constraints on what is the sort of lower limit of dark matter particle mass that we can still have in the universe. Because we do not observe very smooth universe. We see a lot of structure in the universe. There are galaxies, and there are dwarf galaxies, smaller galaxies, clusters, filaments. there is a lot of detail, a lot of structure that we see. So dark matter cannot be too warm. And this is the most important aspect that we can provide from observing the cosmic web, is saying that dark matter masses cannot be too low. They can only be higher than some value. Now, to understand a bit the variety in dark matter models that I showed in one of the previous slides, I will relax the assumption that the thermal production is valid. Or rather, before going to that, I would like to show you exactly how this structure looks like in the observable universe. So I was talking about these gravitational potential wells, how they are smoother in warm dark matter model compared to a cold dark matter model. And what I'm showing here is a simulated universe with a cold dark matter particle on the right-hand side and a warm dark matter particle on the left-hand side. And what you can really see, sort of the first impression that you get, is that there is a lot more detail. There is this image on the right is much sharper, and image on the left is sort of blurred out and smoothed out. And this is really the effect that we are trying to observe in the cosmic web. And we can say, if the structure gets too smoothed out, we can say that the universe does not look like that when we're simulating it. The observed universe does not look so smooth. The observed universe looks more structured. So now I'm going to go to these promised other models where thermal production is no longer valid. And what I would like to convince you is that the general picture still stays the same. For example, in this particular case, instead of talking about cold dark matter and warm dark matter in terms of WIMPs and sterile neutrinos, I'm now talking about something called axions. And the reason why I chose this is just because these types of theories have garnered a lot of interest in the recent years and have been featured on the news a lot. And in this case, the thermal production, the production of this dark matter particle is no longer thermal. It is, in some sense, colder, in the sense that the velocities, the energy distribution of these particles when they're produced is much lower than the energies of electrons and protons. And the dark matter is produced through different channels. In this particular case, the channel is called Paget-Quinn mechanism. And much like us for cold dark matter, we have a favorite candidate in the heavy end where these axions are heavier. It's like a cold dark matter, but instead of WIMPs, we have something called a QCD axion, which is another elusive particle from particle physics world that people in LHC and similar experiments would very much like to detect, because it would solve some of the problems that they have with the strong force theories. And much like cold dark matter WIMPs, these cold axions will also produce a lot of structure in the universe. Whereas on the other end of the spectrum, lighter axions, sometimes referred to as fuzzy dark matter or ultralight axions, on the other hand, produce this very smooth universe that looks very similar to something like warm dark matter. And as was the case before, here as well, we can say something about what is the lower mass that these sort of theories can have based on what we observe in the universe. And we can say that axions cannot be lighter than a given value. So this is very reminiscent of this warm dark matter, cold dark matter scenario before. And the only difference is that the absolute values of these masses are now in a completely different regime, because this is linked to the production mechanism. Another aspect that I would just like to highlight is that while for warm dark matter, what is really driving the physical difference between cold dark matter and warm dark matter is what is the difference in velocities with respect to the mass of these particles. Fuzzy dark matter and axions produce this sort of smoothed out behavior from a completely different physical process. That is because the wave-like nature of these particles is such that it affects the growth of cosmic web. So to explain this a bit better, quantum physics teaches us that any particle can be described as a particle or as a wave, and we can describe this wave with some wavelength, with characteristic size that tells us within this size, it becomes very hard for us to tell where exactly the particle is located. for electron, for example, or for a proton, for hydrogen atom, this size is roughly the size of the atom, or just a bit bigger, which turns out to be something of a fraction of a nanometer. For fuzzy dark matter particles, this size, within which we are unclear where exactly the particle is the size of a big galaxy. And this is the reason why the cosmic web is sort of smoothed out. But in the end, it produces a very similar effect on the cosmic web, and this is the effect that we can see. With that in mind, what I would like to point out is, while we can say that the dark matter particle has to be more massive than a certain number, it is a bit harder for us to tell what is the difference between an axion-like model versus a WIMP or warm dark matter model. But hopefully with better data, we will also be able to distinguish between the two. So what I've been telling you today is sort of three main things. I was trying to tell you how we can unravel the nature of dark matter using various different observational strategies of our universe. I was mostly talking about the cosmic web, but there are many different ways we can learn about dark matter that are in some sense complementary to cosmic web. Some of these are stellar streams or rotational velocities that I've already mentioned. But what I've not talked about is that you can also observe how much light is coming from clusters of galaxies. And we can look for signatures that the dark matter is decaying into photons. And this has also been something of an active research, also here in Cambridge, to understand what is the interaction between dark matter and photons or electromagnetic sector. And then after I talked about the cosmic web, I was trying to convince you that we can map these cosmic webs really well by looking at the distant quasars and observing the intergalactic medium. However, this is not the only way to do it. We can also do this with galaxies, or we can map the cosmic web with cosmic microwave background or weak gravitational lensing. But the reason why intergalactic medium is so powerful is because we can really probe and we can really understand how the density of matter varies from place to place along the line of sight towards a quasar with a very detailed step. So we can very accurately measure these small variations that are a signature of a more cold dark matter model. And then in the end, I was showing you how this cosmic web is sensitive to dark matter particles. And I was showcasing some examples of cold dark matter models, which is our standard cosmological model that we like to work with, and also some alternatives like warm dark matter or axions and fuzzy dark matter models. But these are not all of the models that are out there. In particular, I have neglected mentioning some of the models that have more than one dark matter particle type, or models that have interactions between dark matter particles. And these are all still of very much interest and not ruled out. These are valid models that could explain our universe. And we have many different ways to tackle the question of whether the dark matter is also interacting with standard model like protons and electrons, or whether it's interacting with itself. And hopefully one day we'll also be able to tell how many of these dark matter particles, if it's more than one type, are out there. But for sure, cosmology and astrophysics is really leading the frontier on one part of the nature of dark matter, which is what are the lightest dark matter particles that we can have. Thank you.
Wonderful, Vid. Thank you very much. Really interesting look into like the details of this like super interesting subject, which some people might not have heard of. So there are some fantastic questions coming in already. So some of you have found the YouTube chat box. I think it's this way I'm pointing. And so if you have a question for the speaker, pop it in the chat. We'll start off with this one from Julie, who wants to know that if dark matter is baryonic, does that mean it can't be composed of quarks? Like, could quarks possibly like be a solution to dark matter?
Yeah, so this is a very excellent question. As far as we understand, it is very hard to have baryonic dark matter. In principle, if dark matter is baryonic and it's composed of particles that we already know, such as quarks or electrons or something else like that, we already know that there are a lot of other forces between these particles, such as electromagnetic, weak, and strong force. And it is very hard to reconcile some of these cosmic web structures and other measurements in the universe with a dark matter that is very strongly interacting with everything else. Dark matter that mostly fits our observations is actually dark matter that only interacts with other particles through gravity. And if it has any kind of interaction, it has to be very weak. That being said, dark matter could still be baryonic. It would just have to be very heavy. And people often talk about primordial black holes as a solution to that.
Well, thank you. Another question from Chaminda, who wants to know, do you think that dark matter is going to clump? Like, so do we explain how dark matter pulls on galaxies? Is dark matter going to be clumps in the same way as normal matter, or?
Yes, this is another excellent question, and perhaps I did not explain these very well. But when I was talking about this cosmic web, what I really meant is that this cosmic web that I'm showing here, which is really from our simulations of the universe, it includes both dark matter and the normal matter, sort of baryonic matter. And dark matter, in fact, clusters. Yes, this is indeed what is driving force, because there is more dark matter in the universe. Compared to the normal matter, we have around we have 24% of the total energy is in dark matter, and only 4.6% is in atoms. So clustering of dark matter is really what is driving this clustering in the cosmic web. And this is exactly what we're trying to observe. Yes.
Wonderful, thank you. A question from Libs, who just wants you to clarify something you said in the talk, I think. So they said, if we don't know what dark matter looks like, how can we tell that it's warm dark matter? Because you use this phrase, being blurred out. How can we tell something is blurred out if we can't see dark matter?
That is an excellent point. So it goes back to the fact that what I was trying to point out is, while we cannot observe dark matter directly, we can observe the hydrogen, the intergalactic medium that resides in the same place as dark matter. And where there is more dark matter, there will also typically be more hydrogen. Now, this is perhaps not entirely true, because hydrogen and helium and intergalactic medium has pressure, whereas dark matter typically doesn't. But it still holds to a very good degree that where we have more hydrogen in the universe, where we see more scattering, that's where we also find more dark matter. So what we're trying to really do is sort of relatively weigh places along the line of sight that have more scattering and more dark matter versus the ones that have less. And then we can say something about whether the structures that we see are smoother in hydrogen, and whether this reflects that the dark matter itself, the distribution of dark matter, is smoother. But this is an excellent point, and this is one of the key limitations of this sort of analysis, is that dark matter and intergalactic medium are not exactly the same, but they do follow what happens to one happens to a large degree to the other as well.
Thanks. A question from Richard, wants to know about gravitational waves. We had a talk last week all about gravitational waves. Will gravitational wave astronomy give us any clue to the nature of dark matter?
Yes, I'm really glad that someone asked this question. So I will probably answer it in a way that you won't really appreciate or like it. But by measuring gravitational waves, it's not very easy to measure whether dark matter is warm or cold. What we can measure is how much dark matter there is just by looking at the expansion of the universe, much like people look at supernovae and try to measure how fast the universe is accelerating. People would be able to do this with enough measurements of gravitational waves. However, what really produces gravitational waves is interesting. So these are black holes. If there are some types of dark matter around black holes, we can say something about the mass of the particles by looking at how fast black holes are spinning, because some types of dark matter would spin down black holes. And the fact that we see spinning black holes already tells us that these sort of models are not viable.
Thanks. Question from Wakefield Astronomy. Maybe the whole society is watching along. They want to know if 21 centimeter radio waves are not affected by hydrogen gas, can we use these radio waves to map dark matter?
Yes, so the way we observed what 21 centimeter radio astronomy is actually still looking at exactly intergalactic medium, and even more precisely, it's still looking at hydrogen. It's just not looking at the hydrogen Lyman alpha line, but it's looking at hydrogen 21 centimeter line, which is a transition when the spin of the electron is flipped. But whatever the case of the particle physics, it is actually very similar method. So in that sense, it will produce or be able to produce very similar constraints. And some people hope that by measuring these at further distances from us during the cosmic dawn or the epoch of reionization, we will be able to put even stronger constraints on dark matter and be able to provide even better understanding of what dark matter masses are. But the type of measurement is actually very similar.
A question from Scott. What purpose does dark matter serve in the universe, and does it have anything to do with the universe's expansion?
Yes, so these are good questions. I will try to answer them separately, and I'll first answer the second question. So the way the universe expands, and it's really quite amazing. It does not really matter whether we have dark matter or baryonic matter, or whether we have photons or some radiation. But it turns out that if we throw something into the universe, any kind of matter, any kind of energy, the universe will start to expand as a result. This is the inherent property of the universe. If there is something in it, it will start to expand. So that being said, the way the universe is expanding very much depends on what the ingredients are. So by mapping the expansion of the universe, we can tell how much dark matter there is. We cannot really tell whether this dark matter is warm or cold, because this has to do something about this structure that we see in the cosmic web. And dark matter has a lot to do with this structure, and this is the part that we can measure in the cosmic web, is basically the dark matter cluster. So where initially there is a bit of dark matter, a bit more than somewhere else, this dark matter will, through gravitational force, attract more dark matter. So you will start to grow big clumps of dark matter, and these are for example these knots regions. And in these regions, these are the regions where galaxies will start to form. So the way the dark matter forms this structure is really providing the backbone, these gravitational potential wells in which normal matter then resides and forms galaxies and stars and so
on. Wonderful, thanks. So a couple more questions, if you're happy to.
Of course, yes.
To answer them, we don't keep you talking too long. A question from Julia, who wants to know, does dark matter interfere with things like satellites and spacecraft?
Yes, in principle, there is dark matter everywhere, even in our own solar system. However, from the way what we understand about dark matter, the density of dark matter is very low in our solar system, or compared to other places, like in the center of the galaxy. So it does not really interact that much. However, people are trying to actively search for interactions of dark matter with things on Earth. There are laboratories on Earth, one of them, for example, on Antarctica, trying to see if some unknown particle like dark matter interacts with water or frozen ice deep beneath the surface of Earth. And this is a field of active research. However, it does not really impact the way satellites move around Earth, because this is very much influenced by Earth's own gravity, which is much stronger around Earth than any dark matter in the neighborhood. And even then, the sun is also much stronger, and the galaxy's gravitational pull is next one that is stronger.
Great. So we've got a couple of people in the chat talking a little bit about the possibility of dark matter particles having some charge or some small amount of charge. I don't know if you'd like to comment on that.
Yeah, so there have been recent talks about this milli-charged dark matter. While this is certainly a viable model, I'm not really able to comment much more than to say that some of the observations seem to suggest that milli-charged dark models are in complete agreement with observational data that we have, but it's still unclear how much charge this dark matter can have. In particular, if this charge is really of some dark matter charge, or whether this is electromagnetic charge, is also another question. But this is typically not kind of dark matter that we can learn about by looking at the cosmic web, which is more the area of my expertise.
Okay, and just one question to round out, if you don't mind, again from Charminder. First of all, says great presentation, as many other people are. Some people are saying this is one of the best talks they've seen on here. So well done. Charminder wants to know, what is your take on some alternative theories to dark matter? I know there are various ways of modifying gravity to attempt to explain the effects of dark matter in other ways. I don't know if you could just give us your thoughts on some of those ideas.
Yeah, so of course, I mostly focused on the particle side, or particle nature of dark matter. And by no means is this the only possible explanation for dark matter. As you just said, we could just modify our equations of gravity and gravitational force and avoid having dark matter. One of the main limitations of this approach is that while it is able to explain one observational phenomenon at a time, like rotational curves in nearby galaxies or stellar streams, these sort of modified gravities, theories that modify our equations of gravity, have a very hard time explaining all the data at the same time. And the only way that is really natural, that sort of is very easy for this to work, is if dark matter is a particle. And physicists like natural solutions. That's why I would say that the particle seems more likely, but by no means these modified theories are fully excluded yet.
Well, wonderful. Vid, thank you so much for the fascinating talk, and thank you for sticking around and answering some of the audience's very excellent questions. I hope everyone found that interesting. So just two things to mention before I leave you. First of all, we will have another talk next week. Dr. Emma Curtis Lake will be talking all about the James Webb Space Telescope, which is going to be essentially an infrared Hubble 2.0 launching this October. So to learn what's happening about that, tune in next Wednesday at 7:15. And nothing Cambridge related, but something very cool in space nonetheless. NASA's Perseverance probe is going to be landing on Mars tomorrow evening. And so starting at 7:15, so the same time as these events, you can tune into NASA's website and watch a live stream event, which is going to take you through the landing of this rover on Mars. So if you're enjoying thinking about space, then tomorrow at 7:15, you can watch a robot land on Mars, which is going to be pretty great. So yeah, that's about it from me. Have a nice evening and see you next week. There we go.